So can you see my Excel? So this is so far what we got. So you can check the date and your name and your score. Okay, so also today I'm going to check based on your attendance. Attendance meaning you are actually participating in the class. All right? Okay, so this is how we're going to work. So let me go back to the point. Okay, now we are back to normal. So let me see. Okay, so today we're going to talk about the performance. So when we have a 4G or 5G, 6G, we always matter, oh, how fast is your internet? So how much can you deliver? So we usually say one movie can be delivered in a second, or one movie can be delivered in less than a second, something like that. So to do that, we have the mathematical and quantification for this. So the metric we are using in the network world is bandwidth. Bandwidth is the amount of data transferred per unit of time. We usually use a second, or the amount of the data transferred per link, per end-to-end. End-to-end meaning from me to the server, like a YouTube server to my device, and my device to the YouTube server, okay? And the unit we are using a byte, 1 kilobyte meaning in 2 to the 10 bytes. 2 to the 10 actually is 1024, and 1 megabps, M means 10 to the power 6. So we usually use a K, M, G, T, P. 10 is 10 power 3, mega 6, giga 9, tera 12, and peta is 50. Okay, so we also talk about the throughput. Throughput is data rate delivered by a link and connection or link network. So per link or end-to-end, same as bandwidth. So let's see. In a given time, in 1 second, if I can send this rate, 101010, or I can maybe talk a little faster, 1010101010, something like this. Who is faster in the view of the network? Of course, it is speed. In a given time, I can send more information. So what limits this device? Maybe I can use 1 tera, right? So let's say if I'm connected to the point, I can send very quickly. Then in the end, the receiver's performance, oh, I can receive 10101010, but receiver may be here or maybe not. Why is this happening? Any guess? So while we are not able to have 10 terabyte, and why we don't have a terabyte network? Why we only have a gigabyte network? Why? Any voice? Just think about it. Why is this happening? Who limits?
Because our technology is not been there yet.
I wasn't able to catch it. Can you say that again, please?
My name is Yanshi. Can you hear me?
Yeah.
Yeah. So I think our technology is not been there yet.
So what limits? What technology limit us? That's the question.
For example, the number of lambda, such like that.
Lambda? What is lambda?
Um, okay, I maybe I can make my sentence much better, then I can tell you again. Is that all right?
Oh, sure.
All right.
Anyone else?
This is Roshan. I don't think we need
Okay.
terabyte internet right now. Do we like most of our movies and large files are like gigabytes only? Why do we need a terabyte internet?
Oh. You know, in the NASA, they have like 50 gigabps network. And they are using their facility as a test platform, make a faster network. Okay. So we need this. In the end, we are limited somehow. People always need it faster.
Professor?
Yeah.
This is David.
Okay.
I'm not sure, but like the thickness of the wires that we use for the internet that we put under the ground.
Good try.
Is it limiting?
Okay. Roshan was the second, right? And who was the first?
Yanshik.
Yanshik. Okay. All right. So David says a thickness of a cable. Okay, that is oh, yeah. Yes and no. The answer is yes and no. Let's say I am. Let's simplify the problem. Let's say I'm talking to the David's computer just across my room, and we are only using one router, and we are still able to use only 1 gigabps. Why do we limit it by the 1 gigabps?
Professor, this is
Yep.
Yanshik again.
Okay.
Yeah, so actually every connections are using the frequencies, right?
Mm-hmm.
So if we use terabytes, then the frequency should be much larger than before, the gigabytes. Then the router cannot catch it, I think.
Can I catch it? Okay. Okay. Good point. Anyone else?
I'm Taekyung.
Taekyung.
Okay, so maybe it has to do with cost as well, because terabyte is way larger than gigabytes, and there is way too much cost needed for terabytes for the information to be delivered.
Cost what cost?
In terms of like all the routers to handle terabyte worth of data.
Okay, good point. So maybe I can my opinion. So network is limited by the two factors. One is, let's say I'm able to send this fast, 10101001. Okay, so it's somehow network, and we call this a sender, and we have a receiver. Receiver has to sample. Sample meaning if my information is coming in here, then I'm sampling it. Then based on continuous sampling, I make decision. Okay, I sampled 1, 2, 3, 4, 5 times, and it is all saying 1. Saying I can make, oh, this is 1. Sample, okay, I can make decision. Oh, I sample multiple times. Okay, this is 1. We talk about analog. Okay, all the basic fundamental network is somehow, and it must be through the network, the analog. Why? Your tap, your wire, your fiber optics. There is some point is measured that's delivered by the medium. That medium is analog. Okay, then we have to sample. Whenever we talk, oh, this is the communication. Okay, if this is the communication in the other end, but in the middle there must be the analog. Okay, but analog like we are using air in the wireless network. Analog is the cable we are using. Okay, so we have to have a sample. then we called oversampling, and the factor is a 10. So in today's technology, we're using a 10 times of oversampling. So to make a right decision, this is 1 as 1, I have to confirm more than 10 times. Then I can make decision. Okay. If the majority is more than 7, oh, there is a 10. And there is a 7 1 says, then I can make, oh, this is 1. So what's the issue? So let's say I sent the information as gigabyte. Your receiver should. Okay. Okay. If your sender sending at gigabyte, your receiver has the ability to 10G for oversampling. Okay. Then if the receiver sending, I'm using an Intel gigabyte with the 3.2 gigahertz. This is today's Intel CPU. Then this receiver should have a 10 times more. And it is very tough to have this ability in the user computer. So the clock speed is somehow limited. So what is most precise clock speed? Something like atom watch, atom clock. GPS using an atom clock. Your computer only using chip, Mercury clock. Therefore, your computer is somehow still limited by gigabps. And also, if you're using a wireless, say, so IQ plane. Do you know what is IQ plane? I phase and Q phase. Do you know what it is? It's maybe physics in your high school. No. So how's the voice or how's the air is transferred? So if I'm saying my voice is traveled in the sine wave. Okay. Then in phase and Q phase is usually, so your sound or your electric signal is dominated by in phase and Q phase. So if I want to say, oh, I want to say 1010, then I can say, okay, this is 1 and this is 0. So I'm changing Q phase. Okay, 1 0 1 0. Therefore, your signal look like, hey, 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 hey. Then the receiver may receive, okay, hey, 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 hey. Meaning, okay, this is close to 1 pattern that I'm expecting. Okay, this is close to 0 pattern that I'm expecting. Therefore, I can understand, okay, 1 0 1 0 is delivered. So for that, we are using, let's say it is what I just explained to you is only this phase or this phase. This is BPSK, binary phase shifted key. So I'm using only 1 or 0. What if I'm using QPSK? Quadrature phase shifted key, meaning I can send this, and this information. This is 0 0 0 1 1 1 and 1 0. So if I'm sending this information, my receiver may receive, okay, this information, then I can translate to, I'm just receiving 0 0. Previously it was a 0 and 1 and 0 and 1. Now I'm 2 times faster because I received this pattern. Okay, I received 0 0. If I receive this guy, 1 1. Okay, this is advanced over time, and we are using a QAM, quadrature amplitude modification, meaning so now your receiver is more sensitive. The receiver has this ability to distinguish this pattern and this pattern. So if I receive this information, this is 60 out of 64 pattern. Why? 16, 16, 16, 16, right? If I receive this pattern, meaning 0, 1, 1, 1, 0, 0, 0, 0, something, 64 range. Okay, so there is a 128 QAM2 256 QAM. And there's many mechanisms like this. So your receiver needs to be sensitive enough. Then, so why are we still in the gigabps? Because sensitivity on the receiver. So let me show you the examples. Q, Q, N. So something like this pattern. This is typical QAM pattern. And I may have more complex QAM pattern. And let's say go to the Wi-Fi modulation. Wi-Fi. Go to the Wi-Fi modulation. Okay, so this is standard protocol of the Wi-Fi. You can say, okay, there's OFDM, orthogonal frequency division multiplex, and all information, and it says, oh, where is the start? Let's see, 802.11n. 4. Oh, here's a good one. So modulation type, BPSK. We know what the BPSK we just talked about, and QPSK. Ah, we know what it is. And QAM and DPSK, QPSK. As we have a more and more, it will be more complex, and the network speed is keep increasing. Okay, so we are able to understand this column, modulation type. Why do we have a modulation? Because your receiver needs to have some level of the sensitivity. I cannot just send one information I cannot guess, but we have to have a protocol. Protocol means I have some pattern which the receiver is expected. Okay, so as we have a more and more complex pattern, the speed is increased. In this case, 195. In this case, 195. And is 19. This is 78. From 16 to 64 is 78 and 195. So it's almost double. Okay. So this is why we are using limited network. Okay, it's in wired and wireless. Okay, so let's talk about latency and delay. What's the latency? Latency is the time for sending data from A to B, and how long does it take? Is usually a network, the latency. So we are using a metric second, or a millisecond, or a microsecond. If your network is sensitive enough, it may be nanosecond. Okay, and per link or end-to-end usually consists of TT and TP and TQ. TT is a transmission delay, and TP is propagation delay, and TQ is queuing delay. So we also talk about the RTT, round trip time. From A to B, message is delivered and message delivered back. And we call the round trip time. So one time is a trip time. Come, go, and come back is RTP. Okay, so remember this. We're gonna talk about TT first. TT is a transmission delay, file size divided by bandwidth, meaning I have this cake, and in the middle, my baby is delivering by a dish and delivered to the destination. Let's say it's to father, mother, or my family member. What this baby can do is these small pieces can be delivered on the plate and give it to father. These pieces and deliver to the father. Okay, so whole chunk need to be divided and delivered. In the view of the network, if I have a movie, I have to divide by a small video chunk, then deliver to the receiver. Because your network can handle only this much at one time, at a given time. So transmission delay is usually file size divided by bandwidth. Now you understand this. And propagation delay is time needed for signal to travel the medium distance and speed or medium. Okay, how long does baby take time from cake to the father, cake to the mother, and your video from YouTube delivered to your computer, YouTube to your computer. Okay, and queuing delay, the waiting in routers buffer. Let's say it is not simple. In between YouTube and your computer, there's a multiple routers. So routers has many works to do. So what they do is receive, then digest, and send it to the next. Receive, digest, then send. Then how long does it take in waiting in routers buffer? Okay. So let's see the example. So I have to transfer 1.5 megabyte file. So if I'm using a B as a capital, we assume we are using byte. If you're using a B as a lower letter, is a bits. Okay, so transfer 1.5 megabyte file, assuming RTT is 80 millisecond. A packet size is 1 kilobyte. In an initial handshake, I require 2 times of RTT. So bandwidth is 10 megabps, and data packet can be sent continuously. It can be sent continuously. How long does it take to deliver all my file? So first, what I need to do, 2 times of the handshake. Handshake 2 times. Why do we need the handshake first? So every network needs a connection time. Okay. Oh, can I send it? Yeah, you can. Okay, I'm gonna send this one. Okay, you're good to go. Then I'm keep sending it. Okay. Then how long does it take from this point to this point? I have to spend 2 times of RTT for the handshake. And I have 1.5 megabps. And my file size is 1 kilobyte. 1 kilobyte meaning the dishes that can carry, right? Try to remember this dish your baby can handle, okay? 1 kilobyte in a given wire, which is 10 megabps wire, okay? So 1 kilobyte file dish is delivered by the 10 megabps. Every time it takes 0.8192 milliseconds. And the transmission time is 40 milliseconds. Transmission time, propagation time is actually half of the RTT. From here to here, we call the propagation. And number of packets we have 1.5 megabps, 1 megabyte, which is in the view of the packet, I have 1,536. So initially, I need to have 2 times of RTT, and I have to have 1,536 times of transmission delay. Then in the end, I have to count this. Okay. If I cannot continuously send, I have to count TT plus TP at every time. But in this case, I can keep sending it. Therefore, I only need to care about this TP in the end. Clear? So total time, it takes about 1.4 seconds. Clear? You want me to do it again? Oh, okay. So your job is in a given network, your network is 10 megabps, and your file size, your packet size is 1 kilobyte. So your whole cake, what you need to deliver is 1.5 megabps. And your given RTT is 80 milliseconds. Okay, so what you need to do, you need to establish a connection first. It will take 2 times of RTT. Can I send it? Yeah, you can. Okay, I'm gonna send about this. Good to go. So from here, you keep sending it. So in this environment, it says send continuously. So I have to have 2 times of the RTT for the connection setup. Then I have 1,536 packets. Then I have to count 1, 2, 3, 4, 1,036 times, 1,536 times. Then in the end, I have to count this tail, which is TP, is propagation time. Then it is 40 millisecond plus 160 millisecond plus, and you're in the middle chunk. Therefore, it takes about 1.458 seconds. Clear?
So what
Too
happens
easy?
if some of the packets don't get delivered?
Oh,
What happens if some of the packets don't get delivered out of those 1,536 packets? So let's say like 36 packets get lost or something. Then what happens?
So we're gonna talk about the more complex scenario. So we are assuming everything is, this is lossless channel. Lossless meaning there is no drop, no loss of packets. So we're gonna talk about the lossy environment.
I see.
Good.
And so what's the difference between RTT and a ping or a latency?
RTT and the ping?
Yeah, or latency, yeah.
Latency?
Yeah.
Oh, okay. Latency. So go back to the point. So let's see. So there is a latency and the RTT and ping, many mechanisms. So in this case, we are talking about transmission delay. We understand what the transmission delay is, right? The file size delivered by bandwidth. My cake needs to be divided into the small pieces, then you can deliver. Okay, now I have one piece of cake, and how long does it take? It is go from one point to the others, end to end. Then I call the propagation delay. And queuing delay, if I have some in the middle, there must be forwarded, right? So there's received and digested and forwarded back. Okay, that is the queuing delay. What is you are saying delay, and what is a ping, and what is a latency? So latency is, okay, I sent my information from A to B. This amount may be calculated as a latency. Okay, so in this case, latency and the propagation delay is considered as the same. And the ping time is come and back. Okay, that is more like a 2 RTT. More like RTT, round trip time. So so ping is a little more complex than RTT. So let's say what's the ping does? Okay, are you there? Okay, someone asked me, I'm here, so I'm gonna reply or no. I make decision, okay, I'm gonna reply, then I'm replying. So ping is from here, then there's computation time plus then comes back. It's very close to RTT. Okay, so it all basically under the delay concept. Okay, is it clear?
Yeah, thank you.
Okay. So if it is not clear, you may ask more. Okay, so at this point, everybody clear how I calculate this?
Professor?
Yeah.
Why aren't we adding the queuing delay to the equation?
Oh, so in this case, so point A to B, there is no in the middle. So I don't edit the queuing delay.
Okay, got it.
Okay. So I can make it more complex by adding a router in the middle. So I'm starting from very simple scenario first. Everybody clear? Okay, then let's practice this. So transfer 1.5 megabyte file, assuming RTT of 80 millisecond, a packet size 1 kilobyte. Initial handshake is 2 times RTT. So in this case, after sending each packet, I must wait 1 RTT. How long does it take? So think about for 2 minutes. So this is the reason why I didn't upload the lecture note before the class. So lecture note is full of the question and the interaction. So let's think about 2. What's the answer? How long does it take? So write down on your paper and let's talk about it in 2 minutes. Okay? Okay, guys. Okay, what's the time? Nobody?
Is it somewhere around 124 seconds?
Okay, good try. Okay, let me solve this. So, what's the difference between previous question is, I have to wait 1 RTT every time. So, until here, everything is the same. So I have to do 2 times of RTT for the connection setup. So every time I have to do 1 RTT after transmission. Okay, then I have to do 1 time and 2 times. I have to repeat 1,535 times, and I have a last packet, which is I don't need to wait RTT because I have nothing to send it again. So this is total time it will take. So if I repeat it, up to this point it is same. So RTT is 80 millisecond and transmission delay is this much. and propagation delay is this much. Number of packets I have to deliver is 1,536. Okay, so before I do, I have to connection established. Hey, can I send it? Yeah, you can. Okay, here's what we're gonna do. Good to go. Okay, I'm sending it. It says after sending each packet, I have to wait 1 RTT. So after transmission, I have to 1 RTT. Then I have to TT again, 1 RTT. I have to TT again, 1 RTT. How many times? I have to repeat 1,535 times. And then the last one, I do TT, and I don't have to wait RTT, but this packet needs to be delivered properly. So I have to wait for propagation delay. Okay, so this is total time is 124 seconds. Clear? Everybody see how I solved the simple example? Okay, let's go to the point. So now, the same environment. This case, only 20 packets can be sent per RTT, but infinitely fast. Something like, oh, connection setup, then I can fast enough, infinitely fast, but I can send only 20 of it, only 20 of it, only 20 of it. How long does it take? On the whole packet. Let's spend 2 more minutes. I think you guys see enough how I solved it.
Professor, I have a question.
Yeah, yeah.
This is Minheng. I got confused with the like when we get the question, when we were given the like the file size and the speed. Like how do we know like the either how do we use how do we know to choose either to use decimal or binary? When we get something like megabytes or like the millisecond or everything, how are we supposed to know when to use decimal, like the decimal kilo or binary kilo?
Oh, I don't get it. So what's your name, please?
Min Heng.
Min Heng. Okay. So you're talking about the kilobyte or
yeah, megabyte or something, like when we were given the file size or the speed.
Okay. Oh, okay. So we have to clarify what is byte and what is bits. Okay, bits is 1010, as bytes is 0 to 7. So 8 bits is 1 byte. Okay, so kilobytes meaning 1 multiplied by k, which is 3, and the bytes is in the view of 8, then it is bits. Clear?
Yeah, but when I see the equation for the transmission delay, there is 1024, which is 2 to 10. It's that we're using the binary, right?
Okay. So let's solve this question in very detail. Okay. All right. Okay, I understand your point. I will explain in the next slide. Clear?
Okay.
Okay. Who has the answer? How long does it take? Yeah.
2 RRT, 2 times RRT, plus time of packets, total package, 1036 times time of transmission, times 20 or RRT, plus time of propagation.
Okay. How long? In the view of the second.
No, I didn't solve it, all of it, but
roughly.
I made the equation. I didn't finish it until the end.
What's your name?
Ulukbek.
Ulbek. Okay, good point. So let's solve this. So let's go back to the point. The previous one. I remember this. Okay. I think we should do this again. So it is saying RTT is 80 milliseconds. It is very clear. And transmission time is I have 1 kilobyte, which is I have to convert it to the bits. Therefore, it's 1024 multiply 8. Then I am bits worth. Then I have to divide by my speed. In this case, it is 10 megabps. It's 10 multiplied by 10 over 7. If you remember, this is bits. This is bits per second. Therefore, the result will be second, right? If I just do 1 KB just 1000, which is byte, then divided by a bit, 10 multiplied 10 to the 7 bits per second. Bits and bytes is not dividable. I have to convert a byte to the bits. Then I am using a 1024 more precisely and 8 for the bits. Okay, then I can bits to the bits divided by bits by second. Therefore, I can have a second. Min Heng, is it clear enough? So
yeah.
we have to see what is byte, what is a K, and what is a bit. So when we calculate it, everything needs to be converted to the bits level. Then I can divide it properly. Then I can come back if necessary.
Professor, I have another question.
Yep.
Like the propagation delay, it's the time needed for signal to travel through the medium, right?
Yeah.
Then, like, for every lines from A to B, don't we need to add the propagation delay? instead of adding TP at like once at the end.
Okay, good point. So in this case, the previous examples, the first one, I can send continuously. So I don't need to worry about how long does it take, because I can send continuously, right? Then in the end, I only need to care about this guy, propagation delay.
Why does sending continuously doesn't matter?
Okay, let's see. In the next example, in this case, after sending one packet, I have to wait RTT, meaning sending it, wait for RTT, sending it, wait for RTT, sending it, wait for RTT.
Mm-hmm.
Okay.
But every send has a propagation delay, doesn't it?
Okay, you are a good point, but I am, in this case, in a simpler case, I'm ignoring it intentionally. Why? To transfer faster. So okay, let's see. David made a good point. Thank you. So if I have to confirm it is properly connected, so after 2 times of the handshake, what I have to do, I'm sending it. Okay, oh, I received it well, then I'm sending it. Hey, I received it well, I'm sending it. Okay, this case, every time I transmit, it will take 1 RTT. Right? But
right.
Well, that is waste of time. So I'm using, so I'm sending it 2 times of it. Hey, rather than confirm it, I'm just keep sending it. Okay, which means I started, then I need to care about this point. Then I have to care about this case especially. That's how we solve the second question, and that's the first question. So in the systematical view, if you want to do confirm, okay, my message delivered properly, I have to wait. So after 2 times RTT, is it delivered properly? If I don't sending multiple times, then, oh, confirm, maybe I can send it again. Okay, I confirm. That is a basic case. Go back to the slide. So what it's saying is I can send continuously. I don't need to worry about this propagation delay, but I keep sending it, but in the end, I have to care about this. So next question was, it says must wait for 1 RTT. In this case, sending it, wait for RTT, sending it, wait for RTT, sending it, wait for RTT. There's no feedback. Okay, then it will take 124 seconds. Previously, it only take 1.4 seconds, about 100 times faster. Okay, now we are solving in a little different way. So only 20 packets can be sent per RTT, but infinitely fast. So I have new assumption again. So up till this point, it is all equal. So initially, I have to do connection establish, which will take 2 RTT. Then I have to do 20 times. So I have 1,536. Every time I can send a 20, then 1,536 divided by 20 is about 70. 140 is 13 and
76.8.
120, then I'm 16, right? So 76. So in this case, in one given RTT, I can send the 76. I can send 20, one given RTT. How many times do I have to repeat? Until 76 times. Then I have some remaining, which is 16. In this case, I can send a little faster because I don't need to wait one RTT. Then only TP is counted. Therefore, it's 6.2 second take. Clear? So I'm talking about very simple many assumption cases. Okay, in a given environment, how long does it take? In a given environment, and how long does it take? Clear? David, is this satisfied your question?
Yes, sir. Maybe I have like different understanding of what TP is. Like,
TP is propagation delay. How long does it take from here to here? This is TP.
yeah, it depends on the distance between two nodes, right?
Yes, right. So if we are assuming this TP is fixed in this case, there is no middle router. So if the A goes away from B, it should be calculated differently.
Okay. So
right?
in
So
one RTT, TP is included as well, like the time.
So RTT is 2 times of TP.
Oh, okay, okay.
Clear?
Oh,
Everybody
that's
clear?
Yeah, that's clear. Yeah.
Okay. All right. Thank you. And one more question. So spend 2 minutes on it. So it's all same here, but first RTT 1 packet, second RTT 2 packet, 3 RTT is 4, 4 RTT is 8, and 5 is 16. How long does it take? And it is infinitely fast transmission rate. It's very similar what we did in here. And how long does it take? Spend 2 minutes on it. So I'm gonna pick Jung Ho-jin and Kang Seung-jae. And Peng Kelly and Son Ye-eun and you, Jung-min, 5 of you. I'm gonna pick one of you to answer the question because you guys are the one who's not asked questions yet. Okay, ready? Okay, Ho-jin?
I'm sorry, I'm still solving.
Okay, Seung-jae?
I'm still solving too.
Okay, okay, next, Kelly?
Also, still solving.
Okay, Yeun? Okay, Jung-min? Okay, you're trying. Okay, anyone else? Okay, this is how I solve it. Okay. If I take over my screen. So in the first one, I can send 1. Then in the second one, I can send 2. In the third one, I can send 4, right? Therefore, this, which is 2 times of previous. This one is this guy. And this one is plus this guy. Okay. So do you see how I solve it? So I have to send 1,536. So where am I? So I'm spending 10 times of it, and I can handle it in 11 times. Okay, so go back to the point. So here I have to do 2 times of RTT for the connection setup. I have to do 10 times of RTT. Then the last one is TP. Okay, so if I show you my slide again. Okay, 10 times, then I can send 1,023, and 11 times I don't need to wait full RTT. Then I only need to care about TP, propagation time. Therefore, it ends up
Professor.
Yeah.
But we need 1536, but we end up at 1535. Does that one bit doesn't matter?
Which one?
I mean, back to the, if we go back to the Excel.
Okay, back to the Excel.
Yep. Did you say we end up with the 10 because we need 1536 bit, right? And but when we end up with the 10, we get 1535, isn't it?
So after 10 times, I solve the okay. Let's say this is what I have to send, and this one divided by this guy. So at the first time, I have to handle this much. So after 10 times, I solve the 1,023, and I still have to solve 513. Clear?
Okay.
Right?
Thank
so
you.
after, first time I solved the 1, second time I solved 3, third time I solved 7, accumulately, and after 10 time I solved 1,023, but 11 time I solved 2,047, but I don't need to go to the 11th time. Okay, then after 10 times, I only need 513, which is deliverable in a one transmission, in one propagation, in one transmission, which is one propagation time. So if I go back to the point.
Professor, I have a question.
Yeah.
So you're saying that like we have 513 bits yet to solve, and we will solve that by the propagation delay?
Mm.
Is that what you're saying?
So let me repeat what I'm saying. Do you see my screen? Okay, once again.
So are the remaining bits to be solved in propagation delay?
Okay, so Tajang, give me a second. Okay, here you are. So the question says, so in the first route, first RTT, I can send 1. In a second RTT, I can send 2. And it is fast enough, infinite transmission rate. Okay, infinite transmission rate is I can ignore transmission rate. So let's solve the problem. Connection setup with the 2 RTT. And in the first 1 RTT, I can send 1 packet. In the second RTT, I can send the 2. Then up to now, I just solved the 3. In the third RTT, I can send the 4. I solved the 7. Okay, repeat. In a 10 RTT, I solved 512. Until now, I'm solved 1023. Clear? And now I'm at the tail of it, and what I have to transfer is 513. In a given RTT, I can send 1024, but I don't need to fully use on one RTT, but one propagation time will be able to solve 513. Clear? Then
yeah.
that is why I only edit this TP. Okay, so system says, the assumption says, I have to wait 1 RTT to transfer properly. So in the previously, I have to fully wait 1 RTT, but in the last one, I don't need to fully wait 1 RTT. I can only send it, and I don't need to fully wait for the 1 RTT, which means I can send in a half RTT, which is propagation time. Good?
Yeah, good. I got it.
Okay, thank you. Tajong, thank you. Everybody clear? Can I move on? All right, so let's talk about the latency versus, oh, we are already 11:54. So from here, we are going to talk about next Wednesday. Okay, from here, we're gonna talk about next Wednesday. All right, thanks for listening today, and thanks for your participation. Any question about today's class? No? Okay, so see you on Wednesday. Thank you. I'll upload the video and upload the slide. Thank you, guys.
See you, Professor. Thank you.